Hi guys, in this lecture we'll be discussing about application of Bernoulli's equation. So previous lecture we have already discussed about the Bernoulli's equation. So this has been derived from the Euler equation of motion. So that Euler equation of motion has been taken consideration of the basic law of motion, which is Newton's law of motion. So when any matter which tends to move will have an energy. Okay, so probably it comes under law of conservation of energy. So here we're going to discuss about few applications of Bernoulli's equation. So through your syllabus, there are a numbers of practical applications, but through syllabus we're going to discuss these or few applications. The first one would be venturimeter. So venturimeter is to find the coefficient of discharge. Actually, you can able to find the discharge through the pipes. Right. So the component of venturimeter, though you will be having a practical session on venturi orifice and pitot tube. So this explanation will lead for you to get an idea also in experiment setups. Right. So we have a venturimeter. So the fluid enters into the pipe. So from that pipe the venturimeter tends to converge. So this convergent part is said to be converged, and we will have a smaller diameter of pipe. This is said to be a throat, then it diverges. So due to this change in diameter of a pipe, the pressure gets reduced at the throat and the velocity gets increased. So here you will have a pressure P1, so here you will have a pressure P2. There will be change in pressure compared to P1 and P2. There will be some change in pressure. Due to this change in pressure, the fluid in the manometer tends to differ. So from this change in manometer reading, you can able to find the coefficient of a discharge. So working of a venturimeter consists of a short converging conical tube which has a total inclined angle of 21 plus or minus, leading to a cylindrical portion of a short length known as throat. So this was a convergent cone. So as I said, it was 21 degrees. So and it goes through the cylindrical portion of a short length. So this is a cylindrical portion of a short length. So we call it as a throat. It is followed by a diverging section known as a diffuser having an included angle of 5 to 7 degrees. So this will be at an angle of 5 to 7 degrees. So convergent will be at higher angle compared to divergent. So pressure difference measure between entry section 1 and the throat section 2, usually by means of U-tube manometer. So this section 1 at entry and this at section 2 at throat. So it's been measured with the help of an U-tube manometer. So this manometer is being filled with a heavier liquid or lighter liquid compared to the type of fluid that flows in a pipe. So commonly if you take mercury, so mercury will be inside the manometers, which has a higher specific gravity of 13.6. So the axis of venturi may be horizontal or inclined or vertical. So it depends, it will not to be horizontal always. So it can be inclined or it can be vertical or it can be horizontal. So based on the different sets of arrangement of pipe, we can able to include the venturimeters and find the coefficient of discharge through those pipes. Area of flow in divergent section is increased gradually to avoid the separation of flow and reduce the frictional losses. So if there is a sudden increase in divergence, okay, so it creates some turbulence and again we'll have some frictional losses. To avoid that, the convergent is smooth, the divergent is smooth enough. The value of coefficient of discharge varies from 0.95 to 0.99. So the reading that comes through the venturi, which is the coefficient which will be equivalent to theoretical. So calculate theoretical and actually you can able to find the coefficient of discharge. So it should be nearly equal to 0.95 to 0.99. So there are different types of venturimeter. So horizontal, vertical and inclined, as you already know. So it may not be horizontal, it can be horizontal, inclined or vertical. So the formula to find the coefficient of discharge, sorry, to find the discharge, Q is the discharge. So CD is the coefficient of discharge. So if it's not given, you can assume 0.95. So A1 is the area of section 1. So this is A1, area of section 1. So if you know the diameter, you can find the area of section 1, which is equal to pi by 14 square. A2 is the area of throat. So this is a throat. So this throat diameter, from throat diameter you can be able to find the area of the throat. H is the difference level in U-tube manometer. So due to this pressure difference, so there will be difference in manometer reading. So this manometer reading is being calculated, and H will be the difference level in U-tube manometer. So you substitute and you can able to get the readings. To find the difference level in U-tube manometer, actually X will be the value, difference in mercury level, liquid level. So this is said to be X. So H will be equal to X into SH by S0 minus 1. So this will be the actual formula to find the H. So X will be the difference of a heavy liquid. So we have two different scenarios. So differential manometer contains liquid which is heavier than the liquid flowing through the pipe. So the manometer contains a liquid which is heavier than the liquid that flows in the pipe. So we're going to use this kind of formula to find the H, which is a head. So X will be the difference of heavy liquid. So this will be the X. So from calculating X, we can be able to find the H. Okay, so don't get confused. So SH will be the specific gravity of heavy liquid in the manometer. So here it is said to be an mercury. So specific gravity of mercury will be 13.6. S0 is a specific gravity of liquid in the pipe. So probably if you take for example, take water as a specific gravity through the pipe, so specific gravity of water will be 1. So it is been arrived from the basic properties of fluid. Specific gravity is equal to density of a fluid by density of a standard fluid. So standard fluid always we take water, which is 1000 kg per meter cube. So 1000 kg per meter cube by 1000 kg per meter cube, it will be equal to 1. So it doesn't have a unit. Okay. So specific gravity of liquid on a pipe, so water will be equal to 1. So if you substitute, you can be able to get the value of H. When H is been found, you can substitute in this formula and be able to find the discharge through the pipe. So the second scenario will be the differential manometer contains liquid which is lighter than the liquid flowing through the pipe. So if a fluid is flowing, here would be a honey for an example, which has a higher specific gravity, or if the fluid that flows is also a mercury, so you may not use the same liquid, right? So you can use a lighter liquid. So when you use a lighter liquid, the formula varies to find the value of H. So H, which is a head, will be equal to X, which is the difference in manometer. So this difference into 1 minus SL by S0. SL is the specific gravity of lighter liquid. S0 is the specific gravity of liquid flowing through the pipe. Okay, so by this formula you can be able to find the H head. Substitute in this formula to find the coefficient of discharge through the pipes. So disadvantage of a venturimeter, it is highly expensive, occupies considerable space, cannot be altered for measuring pressure beyond the maximum velocity. So to certain limit, you can able to find the discharge through the pipes. So next is orifice meter. So it is been installed in a pipeline with the minimum of trouble and expense. That's why it is highly specified, but compared to venturimeter, its low efficiency is very low, but price and installation is very easy. It just looks like a washer. a washer that is been placed inside a pipe, a smaller hole. So you would have seen a washer with in a nut and bolt, same like a plate, it's a cylindrical plate. So you'll have a smaller hole, so water flows through the smaller hole. So you'll have a vena contracta. This spot is said to be vena contracta. So where when the fluid gets into the orifice and it converges and then diverges. So at this part the turbulence will be created. Due to this there will be much efficiency will be decreased. Okay. So again we will be having a U-tube manometer. This being fixed at in the pipe and after an orifice plate. So we have some distance calculations. So I'll come across. So I cannot remember exactly. We have some distance at which this tube 1 and tube 2 will be placed. Section 1 and section 2 be considered. It's like 1 times of diameter of orifice or 2 times of diameter of orifice. 0.5, I think so. 0.5 times the diameter of orifice tube and 2 times of the diameter of the orifice. I will check and come back. Okay. Right. Sorry, I already mentioned here. So orifice meter is a device used to determine the rate of flow through the pipes. So we're going to find the discharge. It consists of a flat circular plate which has a sharp edged circular hole called orifice. So this circular hole is called as an orifice. It is a fixed concentric to pipe. So it's a concentric pipe. Okay. So which means the diameter remains the same. I mean the center point for the pipe, different diameter remains the same. So the orifice diameter is generally kept half of the diameter of the pipe. So if the diameter of pipe is 10 centimeter, so the orifice diameter will be 5 centimeter. Generally kept half the diameter of pipe. It is based on the principle as I explained in eventually. So again we have the manometer setups. So the value of coefficient of discharge varies from 0.6 to 0.65. That's why we call this a low efficient. It is economically less space is required for fittings. So next application will be pitot tube. So it's just a L-shaped tube which is used to find the pressure. So pitot tube is a simple device used for measuring the velocity of a flow at the required point in a pipe or a stream. So if you want to find the velocity of a water that flows in a stream, you keep this pipe. So what happens? The fluid tends to flow. So at this part, what happens? The fluid velocity of fluid will be equal to 0. So it doesn't move, right? So what happens here? The pressure keeps increasing. If velocity is 0, nearly 0, then pressure will be increased. Due to this pressure increase, the water level or the fluid level inside the pitot tube gets increased. So with respect to the fluid level increase, we can able to find the velocity through the pitot tube. So which is equal to V will be equal to square root of 2gh. So which h will be the head. So which again can be calculated from the Venturi's. So that's about few practical applications of Bernoulli. So hope you guys have got some idea. Thank you for watching.